So you could see from my title, I'm going to change a little bit the subject, and I'm going to talk about two different objects. One hand side will be gluon scattering amplitudes, and the other hand side Wilson loops. And at the end of my talk, I will try to convince you that these two objects, which are completely different from point of view of hair origin, scattering amplitude versus would-be green functions, in reality are related to each other through very tricky relations. And the fact that I'm last speaker for this conference gives me some advantage. First of all, because we already heard earlier this week talks by James, Paul, and Fernando about the same subject. So what I try to do, I try to put all these three subjects, all these three nice talks into sort of common grounds, and to show you that all these three talks are just part of the global picture. And second advantage, since there is no time limit, you're welcome to ask me any questions, and I'm ready to answer them. Okay, so the outline of my talk looks as follows. So first of all, I will define you the object which I will be considering with, and this will be on-shell gluon scattering amplitudes in N=4 theory. Then I will review what we know about very special kind of amplitude, will be MHV amplitude in V-Kaplan expansion, and this brings us to this Bernd-Dixon-Smirnov conjecture, which already mentioned a couple of people. And then you will see that out of this nice conjecture, you see some new symmetry emerging. And this new symmetry has been dubbed as dual conformal invariance. And later you will see this dual conformal invariance plays a central role in the whole construction. In fact, we do believe that this dual conformal symmetry, dual conformal invariance, somehow gives us some glimpse of some hidden symmetry which has not been explored yet in N=4 theory. So then I will show you how the same symmetry appears with strong coupling, and I basically repeat what Fernando was explaining about here proposals. And finally, after we combine all things together, you'll see that this duality will naturally merge. So let's start from basic things. Again, don't hesitate to interrupt me if you find something unclear. So what we're going to do, we're going to consider a very special object which are on-shell gluon scattering amplitudes in N=4 theory. And by on-shell gluon scattering amplitude, we mean the following. So imagine you have S matrix of your theory. And what we'd like to do, we'd like to consider matrix element of this object with respect to incoming outgoing states. And our incoming outgoing states will be on-shell gluons. So on-shell gluons, they carry quantum numbers which are on-shell momenta, four-dimensional momenta, p. Then, since the states are physical, they carry certain helicity, which takes values plus minus 1, and finally there is a color. So you could think about these three quantum numbers as specifying your incoming states. Well, to anticipate your questions, let me stress right away that since we're dealing with conformal field theory, the object like S matrix is not well defined when you're sitting exactly in critical theory. Therefore, we anticipate on one hand side there will be something wrong on these infrared divergences, and as a consequence, the whole construction will require to introduce regularization, and later on I will explicitly use dimensional regularization. And final comment that one of the reasons why this object attracts so much attention both on QCD and N=4 sides, because basically you could think about this object as being prototype of QCD scattering amplitude. Basically, the dream is that once you will finish with these scattering amplitudes, you will learn something about part of the final QCD answer. But if you're too optimistic. So let me try to define the object. So first of all, you consider the scattering amplitude, and it seems convenient to consider all particles like incoming. So this error means that all particles are incoming. Obviously, sum of all these momenta will be 0, but still they're all incoming. So as I told you, each of these particles carries 3 quantum numbers, and then once you go to multicolor limit, it's turned out to be very convenient to factorize out dependence on the color into such kind of the object. You take trace of the product of matrices, each corresponding to the incoming particles. You take specific order 1, 2, etc. n. You put corresponding trace, and then what you have in front, you have a factor which now doesn't depend on the color, but which depends only on helicity of the momentum. So this object which is shown here in blue, it's called color-ordered planar amplitudes. So they depend only on helicity and moment of particles, and obviously, since we're dealing with bososymmetric objects, there is a bunch of terms which ensure that the whole scattering amplitude will be invariant on the interchange of particles, incoming particles. So what do we know about this object? So there was a lot of discussion about this object, first on QCD and then N=4 theory, and the recent interest was inspired by 2 findings. So the first findings came with the name of the BDS conjecture, and basically had to do with the fact that this gentleman figure out that perturbative calculation of this amplitude reveals some interesting structure, interactive structure. I will describe you later what does this interactive structure means, but basically keep in mind that there's something interesting structure emerged from the calculation of this object to lowest order in Kaplan expansion. Remarkably enough, Alday and Maldacena formulated here prescription for calculating the same amplitude as strong coupling, and what they found as one of the byproduct of here analysis, exactly the same iterative structure emerges strong coupling. So you have two different limits of the same theory. In both cases, you see some interesting symmetry emerging, and then you ask yourself where the symmetry comes from and what's the physical meaning of it. And then I will try to argue that this dual conformal symmetry is a magic word which allows you to explain the symmetry on both sides and then unify this symmetry, global symmetry, which will be valid for arbitrary value of the coupling constant. So let's start some kind of the zoology. Let's try to classify this object. And I remind you, this object don't carry any more dependence on the color of the gluons, only helicity is the momenta. Let's try to classify this object with respect to possible helicity assignment of the gluons. So I told you helicity takes value plus minus 1, and then what you can do, you could consider amplitudes in which all helicities, all by one, have the same values, and then you could show, using supersymmetric relations, that to any other perturbative expansion, these amplitudes vanish. So the first amplitude which doesn't vanish is the one when you have two helicity flipped. So this amplitude, when you have all helicity except two with the same sign, are called maximal helicity valadic amplitudes. Here's the definition. And then if you have more than two helicity flipped, they're called next to maximal helicity valadic, etc., etc., etc. So let's try to see what could we get from this amplitude when the number of gluons, incoming gluons, equal to 4 and to 5. So again, you start playing with different helicity assignment, and then you could easily convince yourself that if the number of gluons is 4 or 5, there is no way you will have balance of helicity different from the one we have shown here. So basically, for 4 and for 5, all amplitude you could get out of these objects are MHV amplitudes. This makes case n equal 4 and 5 special. The first object which looks like this appears when number of gluons is 6 and higher. For example, this is just two examples of the amplitude which are not maximal helicity valadic amplitudes. And in fact, these amplitudes I'm not going to discuss. The reason why I'm not going to discuss this amplitude because they're notoriously much more complicated. And the reason for this is the following. So imagine I want to calculate this amplitude at weak coupling constant. So again, I'm in multicolor limit and my Hooft coupling constant is parameter of the expansion. Then, in general, what you will find is that any order perturbative expansion corresponding amplitude are decomposed into different Lorentz structure. That is the reason why I could write the general ansatz that this amplitude for general helicity is just given by the sum of different Lorentz structures, and each Lorentz structure has its own expansion. The unique and distinguished feature of MHV amplitudes that there is no the sum. There's only single Lorentz structure which emerges, and what does it allow us? It allows us to write this formula with just perturbative expansion. This is a Born term, one loop correction, etc., etc. And as soon as you factor out Born term in front, you end up with a single function of the coupling constant of momentum variables. And in this case, the problem of calculating the whole MHV amplitude it reduces to calculation only of single function. This is the first simplicity. And in fact, it will be this function which I'm going to discuss throughout my talk. So what do we know about this function? So let's start from perturbative analysis.
Sorry, is that included for 5? For 4 points, I'm familiar with. 5 points also included?
Again?
For 5 points
yes,
also?
yes. Assume we're talking about MHV amplitudes. Depending on number of standard points, you always have only a single function appearing. So let me stay for the moment with the 4 external legs, and let's try to calculate this object, just ratio between 4 gluon amplitude, MHV amplitudes versus Born term to any order perturbative expansion. So the first correction has been calculated long ago by Green, Schwartz, and Brink back to 82, and it looks remarkably simple. So what you will do, if you start from perturbative expansion, you will draw all possible Feynman diagrams at one loop level, you sum them together, and then you will find by some miracle that some of all these integrals could be effectively written as single integral. As a single integral described by this diagram, where 1, 2, 3, and 4 denote external particles, and what you have here, you just have standard scalar box. So again, let me stress again, it's not the Feynman diagram that you obtain from an equal force theory. This is some kind of effective diagram, single Feynman diagram, which effectively describe you some of quite a number of one-loop diagrams. So then you go to two-loop level, and then it was shown by Bern, Rozovsky, and Young back to 97 that once you go to two-loop level, the same miracle of conciliation happen. At the end, you could express two-loop correction to these amplitudes in terms of two scalar integrals. And these scalar integrals, again, have rather remarkable structure. They just look like a double box. So you have horizontal box and vertical double box. And once you have such structure emerging, it's very natural to guess that something goes on to higher loops. And then there was this iteration conjecture was formulated by these people back to 2003. I will explain in a second what does it mean. And then, based on two-loop calculations, then people went further to three-loop calculations. They identify what will be continuation, what will kind of the different topology of Feynman diagram you encounter. And here's just a list of 6 different topology of Feynman integrals. Again, you have remarkable simplification of the structure. You have everywhere a box, horizontal 3 box, vertical 3 box. These are called tennis court. And then you see that, okay, it's rather nice. So you start from a very complicated object, and you went to 3 loops, having finite number of diagrams to calculate. And by this, once they arrive to this 3 loop expression, they immediately realize that indeed the structure which was imposed here at the loops, indeed is there. And recently they even went to 4 loops. And for 4 loops, you have much more topologies emerging. These people define them. But still, there is some kind of a very nice structure emerging, and people realize it just having explicit calculation performed. So now let me, so basically this is the transparency which I borrowed from James. Let me again stress you that all this diagram which you have seen in my slide, previous slide, have an intrinsic hidden property. And this hidden property has been first identified by these people just looking at the one loop diagram. So I remind you again that one loop correction to the scattering amplitude is given by a scalar box. And then a priori you would expect to find Feynman integrals like this when you have 4 propagator in the denominator. K is the loop momentum which flowing around the loop. And then remarkable things about those integrals that when you look at this integral, you don't observe any additional structure, any symmetry, particular symmetry. But once you switch to new coordinates, simply replacing p1 by x1 by x2, etc., just introducing some additional dual x variables, you immediately realize that this integral could be written in this form, where x5 just intermediate points, and x1, x2, x3 are 4 external points. And the nice feature about the integral, as James already outlined, that it exhibits new symmetry. And this symmetry is just conformal symmetry with respect to change of the x variables. And since this x variable...
But this is true, I mean, it's just property of this box. It's not related with n equal 4.
It's not related to n equal 4, but the very fact that n equal 4, one loop correction to n equal 4 expresses them with this particular integral, and this integral has this particular symmetry, implies that n equal 4 has this symmetry at one loop.
I mean, if you have 2 boxes, also just 2 boxes have these properties.
Sure, but you better start from one loop. So if you encounter one symmetry at one loop, then you go to 2 loop, you verify whether it's there, the answer is yes. Then you go to 3 loop, you verify it's still there, and then you're optimistic it will be there for loops. But in this example, you just explicitly see the symmetry is there, and then there is a couple important remarks. The fact that these x's are related to the momenta implies that the symmetry we're talking about is not really conformal symmetry of a regional space, because in regional n equal 4 series, this conformal symmetry operates on the coordinates, real true coordinates, whereas here it's operates on the variables which are intrinsically related to the momenta. Well, there is one remark that in principle, when we're doing these transformations, I was tacitly assuming that the integral well defined. In reality, it's not. I told you this external momenta on shell, and this integral in fact develops infrared divergences which need to be regularized. And then what happens that if you regularize your integral putting external particles off shell but staying in 4 dimensions, the symmetry is still there. But as soon as you introduce dimensional regularization by putting here 4 minus 2 epsilon, you slightly break this conformality. And then we later will explore this breaking of conformality, and I will show you how you could make use of this breaking of conformality. And finally, I will show you, by the end of my talk, that this oddly looking symmetry turned out so powerful that it allows us to determine 4 and 5 gluon amplitude to all loops order without doing any calculations. So let's now come to real calculation of Feynman diagrams. So far we just make classification of the diagram. We're sort of ready to accept that there is dual conformal symmetry, but let's look how this expression for the amplitude looks like, this explicit expression. So again, I return back to my favorite example, just one loop correction to the 4 gluon scattering amplitudes. I told you that at one loop level is given by the scalar box. So these are my scalar blocks. A is the coupling constant. And then what you have here, more or less the same integral you have seen before. And there is no problem to calculate it. I introduce dimensional regularization. Dimensional regularization regularizes infrared divergences. And finally, what I expect to find the expression which has infrared divergences. So here you have infrared poles, which appear to the effect. And unusual feature as compared to the field theory, when you're doing calculation of anomalous dimensions, that here you have one loop expression which has double pole. Normally, anomalous dimension situation you have only single pole. But here you have double pole, and this has to do with the fact that if you look for this diagram and you integrate the momenta of these particles, which simultaneously soft and with small angle with respect to either this line or this one, you'll have enhancement what's called soft and collinear singularities, which make normal infrared pole even stronger, which give rise to the double pole. So here you have simple pole with a residue depending on the ratio of modest time variables. So here you have constant term. And again, there is two loop corrections, which I didn't include so far. So then the question is, what will happen if I go to higher loops, for example, 2 loops? And then the answer is known for many, many years. Basically, what will happen at the end, that once you will look for the expression for this amplitude 2 loops, you always will be able to separate infrared divergences into special factors, which I call here divergent factors depending on S, divergent factor depending on T, times some finite remainder which depends on the ratio of kinematical invariance, but which doesn't depend on the parameter of regularization. This is number one. And second point that also it's well known, basically back to the classical paper by Bloch and Orsic 1937, that the infrared divergence is exponentiate. And this feature holds true in any gauge theory, independently whether it's confined, conformal, or whatever. Infrared singularity is exponentiate. And there is another remarkable feature that once they exponentiate, what you have here in the exponent, and this expression here is valid only in equal force theory. What you will have expansion which goes in powers of the coupling constants, where in the exponent you have maximal double pole with a residue here and here, defined by the numbers, with this number being the very same cusp anomalous dimension which has been discussed intensively during this conference, and this being second anomalous dimension, which called so-called collinear anomalous dimension. So basically, it's sufficient to provide information about these two numbers to specify infrared divergences inside this amplitude to all loop orders. And again, let me stress again that this feature has nothing to do with unequal force theory. It's just a universal feature of any gauge theory.
So this G object is some gauge dependent thing?
No, it's this one. This object is gauge invariant. But this object, it depends on the regularization that you introduce for the infrared divergences.
Okay.
But it's gauge invariant. Independently which gauge you're using, it will be always the same.
So we don't really want to know it?
Well, this situation is much more tricky on one hand side. The problem is that this amplitude itself, the fact that it has infrared divergence, it means that it's not physical object. The physical object, the one which you will presumably will measure in the experiment, if one will do experiment in the equal force theory, will be physical cross-section which is finite. And then in QCD, indeed, we know that when you're calculating physical cross-section, you know that individual diagrams do contribute infrared singularities, but they cancel in the sum of all observables of amplitudes. And therefore, at the end of the day, you're expecting that both of the stems will disappear. And what will left over, it will be only finite part. Therefore, you could spend the rest of your life calculating this object here, but at the end of the day, when you come to the physical cross-section, you're more or less guaranteed that it will go away. Well, this is why I call it non-universal. It depends on the regularizations that you will impose to calculate this object. So now the question is, okay, this was very nice, but now what about finite part? And again, what about finite part? Do you expect to have simple structure? And then again, I told you that this question had been addressed many years ago in QCD, and then you ask yourself, well, let's start with QCD. So what do you find in QCD? And here what you find in QCD. So this is a finite part of the 4 gluon amplitude in QCD, calculated to loop level by these people. And then what I did, I performed would-be multicolor limit in QCD. So I separated that factor which dominates in multicolor limit, suppressing contribution proportional to the ratio of quark flavors of number of colors. And then this amplitude A, function of the ratio of kinematical invariance, has this very simple form. Just yeah, it's 2 loop. It's just 2 loop explicit calculation in QCD. And then if you look here, you see here 3 dots because the whole expression fits into 3 pages. And then you're saying, okay, once you have such expression in QCD, you understand that there is no hope you will find any simplification going to higher loops. But then you ask, what will happen in Q4? Lagrangian in Q4 is much more complicated than QCD, but how the finite part looks like. So once you have this, you go to an Q4, and here's the result. So this was the result which exactly subject of this BDS conjecture, which tells you that once you've identified this finite part at one loop level, and one loop level is this double logarithms of S over T, and this double logarithms has to do with the fact that infrared divergence appears double pole. So once you identify this stem at one loop level, this conjecture tells you that once you go to higher loops, what you have to do, you just have to exponentiate the term with a prefactor which is just cusp anomalous dimension. And I remind you, this is just finite contribution to the amplitude. So now if you remember my expression for QCD, you immediately should realize that this is somewhat simple, right? And then it's simply in a number of ways. First of all, in QCD you had very complicated function appearing in front of the a square, whereas here just simple function, log square over t, which has given transcendentality equal to. And then you see that if you expand this exponent, you will find iteration of log square with corresponding power of 8. But once you have exponentiation, you could reduce the problem of calculating the whole finite part just to calculating the prefactor. And in fact, these people did the calculations. They found out by explicit three-loop calculations that the coefficient exactly coincides with the cusp anomalous dimension. And this fact should be very surprising to you. Why? Because we more or less understand the structure of Fred divergences, and there is more or less understanding why cusp anomalous dimensions should parameterize infinite singularities. But there is no reason to expect that the same cusp anomalous dimension will appear in the finite part of the amplitude, because basically the finite part of the amplitude receives contribution from the whole phase space inside the loops, and there is no way to expect why this finite part should be dominated by the cusp anomalous dimension, which knows information only about infrared poles. So this sort of very surprising facts, and moreover, it becomes even more surprising after you realize that this conjecture indeed works to three loops. It also could be extended to n, arbitrary n gluon MHV amplitudes, as was shown by these people. And so far it has been verified to n equal 5 gluon amplitude to loops by these people. But still, after you have this, you have asked yourself a couple of questions. First of all, what was the intrinsic reason why this finite correction is potentiate? Even more surprisingly, why should cusp anomalous dimension appear here? So these are just questions which you should think about. So let's now switch from weak coupling to strong coupling and try to explain you how the same structure appears as strong coupling. And at that point, I just will remind you what Fernando told during his talk. And basically, the starting point is that there is proposal of these guys who just proposed that you could describe the same object for gluon scattering amplitude using RDA-CFT. And after here analysis, they figure out that the strong coupling limit, the scattering amplitude is given by the minimal surface. And this minimal surface has a very nice interpretation when described not the original coordinates of DS5, but in terms of the dual coordinates. And basically, these dual coordinates, what they do, they change the Higgs coordinates to 1 over r. And as a consequence, what was infrared before becomes ultraviolet. This is number one. And second, this minimal surface turned out to be minimal surface which are spanned atop of this contour, which are built out of light-like segments. Each of the segments basically defined by the momenta of the external gluons. And so you have this minimal surface. Once you have minimal surface for this configuration, then you identify the position of the corners with the momenta, and then you're done with the minimal surface. And then the very fact that you're dealing with the conformal theory, sigma model, classical solution motion in the conformal theory implies automatically that this minimal surface will know about conformal symmetry of regional theory, which in this case translates simply into the fact that this minimal surface itself, it will know about dual conformal invariance. It has dual conformal invariance built in. Again, as I mentioned to you, that now infrared divergences of the amplitude are translated in ultraviolet singularities of the minimal surface, and ultraviolet singularities are known to be associated with the cusps. So the fact that we have here cusps and integration paths gives rise to very specific so-called cusp singularities of this minimal surface, which later translate to infrared divergences. This is basically the reason why, at the end of the day, you find that infrared poles are accompanied by the cusp anomalous dimension. And again, I could repeat the same words, that if this minimal surface were finite, then it would inherit SO24 conformal symmetry of the aligning sigma model in dual variables. And therefore, this symmetry will be there. But the fact that you have to introduce regularization to deal with these cusp anomalous dimensions, cusp singularities, you're obliged to introduce dimensional regularization, and dimensional regularization slightly violates this symmetry. So the situation is very much the same as at weak coupling. And after you calculate the minimal surface for the case of the rectangle, or if you wish for gluon amplitude, this becomes the result. And the result looks remarkably similar to the gauge series side. Namely, you factorized amplitude in the product of two factors. One of them carries singularities, which means infrared divergences with particular coefficients shown here. And the second factor is just the finite path. And then you immediately realize that coefficient from the double pole, which from weak coupling expansion ought to be gamma cusp, indeed coincides with the prediction for gamma cusp of strong coupling. where this becomes non-anomalous dimension, this prototype of this G. And this becomes sort of strong coupling prediction for this non-leading pole coefficient. And again, this prescription, in fact, it works for arbitrary number of the gluons, 4, 5, etc., etc. The final result is not sensitive to the polarization of the gluons, and it's believed that this sensitivity will appear after you include corrections 1 squared of lambda. And then what happens that the agreement, now you could compare this formula with what you expect from BDS ansatz, and then Alday and Maldacena observe that starting from n equal to 6, here formula for strong coupling expansion doesn't really matches what you expect from BDS ansatz, and therefore the general consensus is starting from n equal to 6 and higher, something should be modified. And at the moment we don't really know what should be modified. But again, if you want to summarize this result, you still have to answer a number of questions. This formula just came out as a result of the calculation, but still there is two surprising features which are there, namely that final correction do exponentiate. And again, the prefactor here is again the cusp anomalous dimension. And then you ask yourself the same questions: why should this feature should appear both at the weak and strong coupling? Who is responsible for this nice feature? And here comes the answer. Okay, not the answer, it's a proposal for the answer. So let's try to summarize what have we learned from a weak and strong coupling calculation about scattering amplitude. So we were dealing with the 4-gluon scattering amplitude, and then what we found that infrared divergences of this amplitude somehow related to the ultraviolet singularities of the Wilson loop with cusps. In that case, we see Wilson loop naturally appearing at the level of divergences. And moreover, we have seen at the level of weak strong coupling that somehow the corresponding Feynman integral at weak coupling have dual conformal symmetry. At strong coupling, the same dual conformal symmetry becomes feature of the minimal surface which you will construct in the dual variable. And now just ask yourself whether it's possible, just using as the symmetry of the objects and taking into account these two features, to construct the object inside an equal force theory which will automatically know about these two properties automatically. So I want to construct an object for which these two properties will be automatically there. And the object is here. So the object is just Wilson loop. And this Wilson loop is defined in standard way. So you have trace, password exponential. Here you have circulation of the gauge field along contour. And this contour is very special one. Basically, there's a more or less the same contour which Alday and Maldacena encountered the strong coupling. But now I'm dealing with this axis just being my normal coordinate in Minkowski spacetime. So this object here is defined in coordinate representation in Minkowski spacetime, with axis being some coordinates in Minkowski spacetime. And the only thing that I require is that all these segments here should be along light cone. And by the end of the day, what I will do when I will dealing with the gluon amplitude, I will calculate the Wilson loop. At the end of the, I will substitute the difference between these coordinates, just these segments, with the gluon moment. So the first thing which you have to note is that this Wilson loop has 4 cusps, and number of cusps is equal to the number of external legs. And therefore, you shouldn't be surprised that there are special cusp ultraviolet singularities which you have to deal with. And again, I will introduce dimensional regularization, and dimensional regularization automatically will produce poles in parameter epsilon, which will describe the singularities. And second remarkable feature is that since this Wilson loop will be calculated in configuration space in an equal force theory, you have possibility to apply apparatus of conformal symmetry of an equal force theory to tell something about properties of the Wilson loop. Namely, what I will do, we will try to study manifestation of conformal symmetry of my theory in original coordinates from point of view of the properties of the Wilson loop. So these are the scheme. So let's start with some symbol exercise.
Why couldn't you do the same with amplitudes? Why couldn't you original?
Good question. But let me postpone this question to the end. Because basically the answer will be the following. If you will impose conformal symmetry in momentum space, and you require that this should be property of scattering amplitudes, you will find the constraints which are much weaker than the one which I will produce in the end. But ask me at the end, I will explain why. So let's start from, again, from symbol exercise. Let me show you that this object, like Wilson loop, in reality is a very simple object. And to convince you, let me start performing calculation of this object to one loop level. So what I will do, I will use definition of my Wilson loop. You remember it was password exponential, so I expanded to second order in G square, and then I contract gauge field to find the propagator, and then basically at one loop level, the Wilson loop is given by the double integral of the gluon propagator with x and y being point on the contour. And again, this object is gauge invariant, therefore you are right to choose any gauge, and technically it's simple to choose Feynman gauge. So this becomes the propagator of the gluon in Feynman gauge. the configuration space. Note that here is the power -1 plus epsilon. This epsilon just parameter which will regularize singularities. And then if you substitute this expression in there, what you will find basically 3 different kinds of the integrals. And what this diagram is supposed to show, this double line integration contour. Here you have a gluon which propagates between any 2 points of the contour. You may have this possibility, or this one, or that one. And then the fact that you have Feynman gauge, you could show immediately the diagram equal to 0. This diagram turned out to be finite. It's only this diagram which becomes divergent. And then it becomes one line calculation to show that this diagram just gives you this. So what you have here sum of all cusp points, and each cusp point, basically this diagram here, produce your double pole, and this pole ultraviolet one, because it comes at short distances in the vicinity of the cusp, with a residue given by mu square power epsilon. Here what you have here, this is just the distance between adjacent points. Very simple. So there is some finite part which you will see on my slide, next slide, but basically it's just the result of one loop calculation. It's really simple. So what you do next, you go to the next step and you now try to compare this object we just calculated with scattering amplitude. I told you scattering amplitude becomes the contribution of scalar box. So now let's try to compare 2 different expressions. The first expression is just the one you have seen on previous slide, divergent part, and here is the finite part, which log square of the ratio of corresponding distances on the Wilson loop, plus constant term, which I don't show you. And here, this line, just the result of the explicit calculation of scattering amplitude. So these are 2 completely different objects. But now when you compare them, you should be surprised to see that they are similar. So if you identify infrared singularities here, the ultraviolet singularities over there, identify the corresponding parameters following this rule, you immediately find the divergent piece match. In fact, there is no surprise because I told you that there is 1-to-1 correspondence between divergent pieces. But what's surprising is that finite part match. So this finite part, which was function of kinematical variables s and t, now matches corresponding finite part, which is function of the distances on the Wilson loop. And as soon as you identify the distances this way, you immediately see that there is complete match. So these 2 completely different expressions turn out to be identical after you make this particular identification of the scales and the parameter. So this becomes the first surprise.
The Wilson loop is also n equals 4 squaring.
Say again?
The Wilson loop is also for n equals 4.
Well, the remarkable feature, this result here, it holds true in any gauge theory, because the fact that you have dealing with supersymmetric theory will appear for calculation of the Wilson loop starting from 2 loops only. At the level of 1 loop, Wilson loop doesn't really care whether you have supersymmetry or not. What's special about this relation is that amplitude will be different if you go from equal 4 to another theory. And therefore, this relation holds only equal 4. But Wilson loop doesn't care whether you have supersymmetry or not. So now comes wild guess or proposal that once you have such a match between the 2 things and you know that symmetries of both objects are the same, namely you have conformal symmetry for Wilson loop versus dual conformal symmetry with scattering amplitude, singularity matches, the only things which you don't know finite part, but still let's put it as a wild guess. So let's impose the following proposal. So let's, basically symmetry, we made a proposal that logarithms of the 4 gluon scattering amplitude in the multicolor limit should coincide with the logarithms of this Wilson loop up to the terms which will vanish if you remove regularization. And in fact, this relation, if you look carefully into Aldheim-Maldacena paper, they hinted that the relation should be there. Basically, what they wrote in their paper is that in the middle of the calculation, they found that calculation of scattering amplitude via IDF-CFT is mathematically equivalent to the calculation of Wilson loop. So basically, what we are saying here, it's not mathematically, it's even physically equivalent to this. So how to check this relation from weak coupling? So at 1 loop level, you've seen that it's more or less obvious. Now let's try to go to 2 loop level and to see whether it's there. And this is where supersymmetry will be important and where the miracle will happen. So what we did, we start looking for the 2 loop correction to the Wilson loop. Again, what you do, you just draw your Wilson loop. These were just 1 loop diagram, which you have seen on my previous slide. And now we're 2 loop diagrams. So the 2 loop diagrams have the following topology. So here you have insertion of a bunch of loops, gaugina, scalars, whatever inside the gluon propagator, the same as here. So here you have just crossed gluon propagators, and here you have diagrams involving triple gluon vertex. So you have a bunch of diagrams. Then what you do next, you calculate diagram by diagram, each of them separately. And then you will find that, for example, this diagram, which seems to be the most complicated one, its contribution to the finite part expressed in terms of some integrals. I have shown you integrals, so believe me, this expression for this integral just take 1 page. But then what will happen if you sum all contributions together, you would see this just massive cancellation of such integrals, and as a result looks remarkably simple. So even at two-loop level calculation, you see something magic happen. So therefore, by this calculation, we sort of convince ourselves that duality is there to two-loop for gluon amplitudes, and then you go further. So once you see that this duality holds true for 4 gluon amplitudes, you may try to generalize this relation for 5 and more gluon amplitudes. And in fact, as was shown by Brandhuber, Heslop, and Travellini, that if you now consider this relation, comparing logarithms of MHV amplitude with arbitrary number of gluons versus logarithms of the Wilson loop calculated of the contour with just made of n light-like segments, you will find that at one loop level there is much perfect agreement. And the same relation also is hidden inside Alday-Maldacena construction. The only tricky point is that once you go through Alday-Maldacena construction, at some moment you will have to calculate the minimal surface which corresponds to this contour. And so far, nobody was able to present explicit construction for n equal 5. And this seems to be technically difficult point for string calculation. Again, what we did next, we asked ourselves whether this relation could be justified at first two-loop level. So at one loop level, it was shown by these people that indeed it's there. And then we made next step, so we went to calculate two-loop corrections. And now you see that full glory of Feynman diagrams. You have pentagon, you have much more complicated structure, especially this diagram is also complicated. And still, calculating all the diagrams, as a result of massive cancellation, you confirm BDS on that. One more miracle. And still, okay, you see many miracles, but still there should be explanation. And now the question arises, either we present solid argument which allows us to describe all these magics right away, or we just bound to say that these properties just are there to 1, 2, 3, 4 while loops, but we don't have any proof which goes through higher loops order. And here's the proof. So basically the proof is based on the so-called conformal Bort identities. So let me emphasize you that once again, that what we're going to do, we're going to take for granted the duality between gluon amplitude and Wilson loops, and then we will start to explore conformal symmetry to understand the structure of Wilson loops, to return back to the gluon amplitude and make certain conclusions about finite part of the gluon amplitude. And here's the idea. So let's start with light-like Wilson loop defined in n equal 4 theory with the contour made of n light-like segments, and let's try to see what kind of the constraints the conformal symmetry of n equal 4 theory will impose for this object. So what we're dealing with very special contour. I remind you this contour SYM, contour made of n light-like segments, is a very special one. It's special in two respects. First of all, you ask yourself, what will happen? Imagine I'm performing conformal transformation in my theory. So imagine I know that this Wilson loop is finite, or suppose it's finite. Then if it's finite, you apply conformal transformation, and then since the series is conformal for dimensions, what you will obtain that the Wilson loop should stay the same. It's basically equal to itself, provided you deform this contour according to conformal transformations. And then if you start here with arbitrary contour, the deformed contour will have some ugly form. So now case we have special situation, this contour is special one, so it's made out light-like segment. And then it becomes as a first surprise that after you perform conformal transformation, you will find that what you obtain here, you obtain the contour of the same kind. So you start with light-like contour with n segments, you perform conformal transformation, you end up with the same kind of the contour. So therefore, if this Wilson loop were well defined in 4 dimensions, this would be the relation which we exact to any order perturbative expansion. However, I have seen you already that the fact that there is cusps induces specific cusp singularities. And therefore, if you really want to give meaning to this object, you have to introduce regularization. But at the moment when you introduce regularization, you break conformality. And then the question arises, how conformality of the theory together cooperates together with singularity of the object. And here is the answer. And turned out that by the end of the day, when you look for the analysis, you will find that under conformal transformation, the fact that there is cusps inside the Wilson loop brings you a very specific contribution, which we call cusp anomaly. And this cusp anomaly modifies transformation properties of the Wilson loop, and it will be this cusp anomaly which will allow us to fix the finite part of the Wilson loop and later finite part of the scattering amplitude. So let me first summarize the result, and then on the next slides I will show you how you could obtain this result from first principles. So what you do next, you start from the Wilson loop, and I told you it's very convenient to split the object into finite part and ultraviolet part. And ultraviolet part, here we mean all the poles and epsilon which will appear due to the cusps. And here you have this object which is a finite part, which doesn't depend on any regulator, and exactly this object which interests us. Then, if you go through conformal analysis, what you will find that this finite path satisfies this conformal word identities. First of all, there is dilatation word identity, which basically tells you that this function of n is dimensionless function of the ratio of the coordinates. This is just not much helpful. But it will be this relation which becomes crucial. So this is a conformal word identity with respect to special conformal transformation. And once this conformal word identity tells you that if you apply this particular differential operator, which acts on the cusp point of your Wilson loop to the finite path, what you obtain here on the right-hand side, very special function which has gamma cusp, which carries dependence on the coupling constant, modified by certain function which depends on the distances. So this relation becomes crucial to find Fn. And then you have heard earlier this week, a strong coupling, this gentleman also argued that basically the same relation holds true as strong coupling. So you could think that this relation just exact relation for the Wilson loop, which valid for arbitrary value of the coupling constant. So how to get this relation? So the derivation basically goes through standard procedure, although I don't know whether it's standard for everybody in this audience, but let me remind you the procedure. So let's start from Wilson loop and write representation for the Wilson loop as path integral. So you have n equal 4 theory, you introduce dimensional regularization. So what you have here, you have Wilson loop, just integral of a gauge field along the contour, weighted with the measure in your theory. So you have integral of all fundamental fields on your theory with action, which dimensionally regularized action n equal 4 theory. Here Lagrangian, you have gauge piece, gaugina, scalars plus gauge fixing plus ghost, depending on your gauge. And then what you do next, you basically change variables inside these functional integrals. So you start with all these fields, and then you perform inside the integral changes the variables going from original fields to the fields which are obtained from original one by applying the conformal boost, and simultaneously you apply this compensating coordinate representation. So since you did a change of the variables, nothing changed. Therefore, variation of the Wilson loop equal to 0, but the 0 comes about as contribution of two terms. The fact that you perform transformation of the coordinates transforms the contour, and variation of the contour is described by this derivative, first term. And second term, the fact that you put here not d4x but 4 minus epsilon, variation of this measure brings you additional factor which appears here. So this Lagrangian with this integral is just reaction of the action under conformal transformation. So at the end what you see, the identical change of the variables give you 0 equal to the contribution. First of them describes action of conformal boost on the Wilson loop, and second one involves integral of the insertion point of the Lagrangian inside vacuum expectation value. And notice two things. Here you have x nu, this position of the x, and here you have epsilon. So this epsilon appears due to the fact when epsilon goes to 0, we remove regularization and theory becomes conformal. But if you have epsilon from different from 0, it just stays here. So if this integral is finite, you put epsilon to 0, and then you will recover the Wilson loop satisfies normal conformal word identities. And we know a priori is not the case. So therefore, this term does contribute. And the fact that there is epsilon allows us to calculate this correlation function, expectation value, only at the level of divergent paths. Because if you will put here a finite piece multiplied by epsilon, it will always vanish when epsilon goes to 0. So this becomes the first simplification, that in order to calculate this integral over here, it's sufficient to calculate this expectation value only at the level of divergent pieces. So how to do this? So again, you start with Feynman integrals corresponding to one loop contribution to the Wilson loop, and now the fact that you put here Lagrangian, as was shown by Belitsky and Müller, simply amounts to modifying the gluon propagator. So you have gluon propagator, just put here some point x, with just point of the insertion, and then you just calculate these three diagrams.
You get the same identity if you include scalar coupling.
Where?
To the BPS Wilson loop.
Here.
Yeah.
Sure, sure. The only difference will be that if you put here scalars, you ought to have the contour not light-like. But if it's not light-like, then this operator will look differently. The advantage of this having this contour light-like, because basically what left over from the information about the contour just position of the point. It's sufficient to provide you endpoints if the contour is uniquely specified. Whereas for the configuration, you have to really put here variation of the Wilson loop. And if you start from some ugly-looking Wilson loop, you go to another ugly-looking Wilson loop. Then here you will have basically variation of this Wilson loop, which you wouldn't be able to control as a function of finite number of points.
This relation is kind of complementary to analog of whatever McKean duality, right?
In fact, if you look for McDowell-McKean correlation, this loop equation, I mean, normally this equation are written in 4 dimensions. So this relation in 4 dimensions becomes trivial In 4 dimensions, you just don't have these terms, and basically when you look for the loop equation always have been written in the version of the theory which doesn't have any singularities. Basically, either you regularize the theory, and you're dealing with Wilson loop abstract objects which are defined in theory 4 minus epsilon dimensions, and you don't care about singularities. Or you're talking about contour which is smooth one. And for smooth contours, there is no any additional singularities that indeed can be defined in 4 dimensions. But here we're dealing with a special contour which has light-like nature, and therefore there is a lot of singularities addition. And these singularities will interfere with this epsilon term here to provide finite contribution. So therefore these word densities become anomalous. That is the reason why we called this contribution here as cusp anomaly.
Equation is
It's not loop equation.
Yeah.
Yes.
I mean, if you
Yes.
consider loop
Yes.
equation, you will get only the first term without.
No. What's loop equation? So imagine, this is just smooth contour, not necessarily circle. So when you're obtaining a loop equation, what you're doing, you're saying, let me apply the operation which put here some small bit of the contour. And then you're looking for the difference between these two guys. And then you expand this small loop on powers of the area. The area will bring you sigma mu, f mu, and the point of the insertion. And then you smart enough, you choose special operator which acting on this insertion will give you equation of motion, and then you obtain the loop equation. Now what I'm dealing here, and this loop equation, it's the whole magic is that you make a local variation of the contour. It's a local variation of contour at the point. Now let's consider my contour. So my contour is contour which are defined uniquely by the points, right? So imagine I fixed all points, and now what I want to do, what this derivative tells me, I'm just doing small deformation with respect to x. So I take x2 and I shift a little bit. And this small variation of the points induce global deformation of the contour. So therefore this derivative, which you have in this equation, is not this derivative. Therefore the equation looks similar, but the nature of the equation is completely different. So now what happens when you put this insertion of the Lagrangian? If there were no insertion of the Lagrangian, you've seen already that this diagram gives you double pole. So now you insert the Lagrangian, and then you're expecting there will be double pole as well with some additional decorations. And these decorations are shown here. So basically what's written here in these brackets is just the result of the calculation of the insertion of the Lagrangian into expectation value of Wilson loop. And then you have double pole and have simple pole. So the double pole has very peculiar structure which tells you that the rate is different from 0 only if x equal to xi. And you remember that xi, it was position of the cusp, and x insertion point. Basically, this delta function tells you that you could get double pole singularity only under condition if you insert the Lagrangian in the point when you expect singularity to occur. And singularity will occur either at the cusp, which is indicated here, but there is additional source of singularity. And this additional source of singularity has to do with the fact that it's possible to put Lagrangian insertion on one of the edges, and still you will have divergent contribution. So these two terms here, this one, gives you dominant contribution which localized on the cusp, and this epsilon function gives you contribution which localized on the edges adjacent to the cusp point. And again, I remind you just the result of this figure one loop calculation. It's just a question of spending some time to reproduce the result. So now once you have this expression, what you do next, you go back to my conformal word identities, and then you integrate this guy with the weight x nu multiplying by epsilon. Multiplying by epsilon, you transform double pole to simple pole. This becomes the final contribution, and here becomes the result. So the result is the following one. So this k nu is just this differential operator which acts on the cusp point. Here you have a simple pole, sum of the cusp point. This term originates from this one, whereas this term does not contribute. And the reason why it doesn't contribute is a very interesting one. So if you start with this expression and you integrate over x, you obtain the expression like this, but then when you sum over y, you find sums to 0. So contribution from each cusp is different from 0, but only after you sum over y, you obtain 0. So then what you do next, you try to generalize this relation to loops. So how to do so? Basically, we have some intuition how to parameterize the poles appearing here, and then based on this intuition, with some analysis, detail we find in the paper, we finally came up with the following relation. So the claim is that this relation is exact to all order in coupling constant. So what you have here, just analog of this relation. Simple pole here, just analog of the simple pole parameterized by the cusp. And this is just basically the consequence of the fact that Caspar anomalous dimension APS is coefficient double pole. So here you have new anomalous dimension, which are analog of this collinear anomalous dimension, which appears as a constant term. And this epsilon term doesn't contribute by the same reason. So this relation becomes exact to all loop levels, to all loop orders. And now once you have such nice relation, you split into finite part, divergent part. You know everything but the divergent part. You know differential equation for the whole object, and then you would obtain differential equation as a function for the function of n, which you have seen in my previous transparency, and then you solve it. So finally, the end of the story is that you obtain differential equation for the finite part of the Wilson loop, which you'd like to solve. And then once you try to solve this equation, you will find some number of other surprises. The first surprise is that if you solve it for n equal 4 and n equal 5, you will find that this equation alone uniquely fixes the form of the finite term. Basically, if you solve it for n equal 4, you will find that this becomes the unique solution model of the constant term. And the reason for this is that the fact that you're dealing with light-like contour basically reduces the number of dimensional parameters. And since for n equal 4 and n equal 5, there is no way you could construct harmonic ratios, then conformal identities just basically fix uniquely the solution. So this becomes solution for n equal 4, this solution for n equal 5. Now you understand that gamma cusp should be there because it was part of my conformal identities. What's not trivial is that conformal identities uniquely fix the form of the function, log square here and the product of logs here. And again, you look for BDS ansatz, and you see that exactly the same expression appears as a part BDS conjunction after you identify kinematical variables. So at this moment, we conclude that conformal symmetry of the Wilson loop allowed us to fix the finite part of the Wilson loop, and then applying this duality between Wilson loop and scattering amplitudes, we deduce that the same function should parameterize the finite part of the scattering amplitude, which exactly agrees with BDS ansatz. So now you go to high number of points, let's say 6, and then you immediately realize that starting from 6, you do construct conformal ratios. So you have 3 dimensionless variables constructed out of the distances, and you could easily verify that they stay invariant in the conformal transformations. And the fact that they stay invariant, it means that there is no way you could obtain dependence of Wilson loop on these variables using conformal word identity. As a consequence, starting from n equals 6, the solution to conformal word identity, so you conformal symmetry of the theory, doesn't allow you to restore the dependence of the final part on these 3 variables. And again, if you try to test BDS ansatz, you could easily verify that BDS ansatz goes through the conformal word identities, in the sense that if you start with BDS ansatz and you plug into word identities, you'll find 0, which doesn't necessarily mean that BDS ansatz is correct, because you always have a freedom in choosing function of 3 variables. But again, the question is how to fix these functions. And this so far the question.
Would it be any simplification which you could get from this equation considering say n or mental structure?
From equation alone, there is no way, because basically the differential equation doesn't care which limit you're taking. But there's another assumption, there's another condition you could impose on solution based on another, let's say, another conditions. One of the conditions is the following one. It goes under the name of the collinear limit. So imagine you consider scattering amplitude with given number of external particles, P1, etc., Pn. And then you take 2 particles, I and I plus 1. And then you want to consider special limit when these 2 particles form small invariant mass. Or if you wish, this momentum Pi and Pi plus 1, the collinear line, almost collinear line. Then there was analysis performed by Bernd, Dixon, Kosover, and other people, and they have argued that if you go to the limit when Pi becomes collinear to Pi plus 1, this amplitude, which is defined as n gluon scattering amplitude, could be factorized out into amplitude which has 1 external particle less, but one of the gluon momenta being just sum of 2, multiplied by the universal object, which are called splitting amplitudes. So another way, this collinear limit allows you to explore the relation between scattering amplitude with n external legs versus scattering amplitude with n minus 1 external leg. And now we would like to understand whether similar relation holds for the Wilson loop. And for the Wilson loop, again, what you do, you draw corresponding image of the amplitude. Namely, you take all the external momenta, you put them as edges of your Wilson loop, And then this limit, the fact that these two vector collinear, amounts to saying that these points moves a little bit to the left in such a way that it will lie on the light-like direction between these 2 points. So it's like flattering one of the cusps. And once you make this lane straight, you effectively go down to the Wilson loop, which has one segment less times the very same universal function factor r. And then, from this point of view, this collinear limit is well understood in physical terms. This is just property of Feynman diagram. And then you ask yourself whether Wilson loop cooperate, whether the same relation could be verified from point of view Wilson loop. And indeed, if you put here n equal 5, which means a relation pentagon down to rectangular, since we know the loop expression for this object and we know the loop expression for that object, we indeed verify that this r function appearing here is the same as r function appearing there. And once you know this, you could supplement the whole construction with additional condition that collinear limit should go in this direction. And this becomes a very strong condition, which basically tells you that the function of these 3 variables which you're supposed to encounter should be function very special, should vanish when each of these variables is going to 0. There's another limit which goes under the name of the radial limit, and Professor Lepatov explained earlier this week. And if you go to the radial limit with the same ansatz, you could argue there's another condition for the same function coming from the consistency condition for the amplitude to exhibit correct radial limit. And this becomes another condition for the functions for each of these u's going to infinity. So basically, you're talking about differential equation for the function of 3 variables. You don't know how this additional function look like, but you know what will be additional condition you have to impose on this function. So this brings me to the conclusion. Basically, the conclusions are very short. What we learned that planar gluon amplitude possess some intrinsic symmetry, which is dual conformal symmetry. We know how to explore the symmetry. Basically, using this duality I have shown you, we were able to construct the finite part of the amplitude for 4 and 4 gluon amplitudes to all loop levels. Again, you have conformal identities. For 6 points, we know that conformal symmetry is not sufficient one to fix the finite part. One needs something more. But there is a couple of questions. First of all, we don't really understand what's the origin of this dual conformal symmetry out of scattering amplitudes. And then there's very good reason to expect that it has to do with integrability. And then if you ask me the question why, I will explain you. And again, what I'm telling you is that if you want to make it very solid to answer these questions, indeed, you have to work more. And finally, my last conclusion is that since I'm last speaker for the conference, let me thank the organizer for the wonderful workshop. Thank you.
Did somebody verify that this BDS amplitude has correct analytic properties?
Yes.
Verified?
Yes.
Exactly.
Okay, what we did, let me show you what.
For example, Steinman relation is fulfilled.
Say again?
Steinman relation is fulfilled.
What is Steinman relation?
Steinman relation is absence of singularities, simultaneous singularities in overlapping channels. Because it is suspicious that if you put everything in exponent, then
Yes.
if you expand this,
Yes.
you obtain, of course, singularities, simultaneous singularities in overlapping channels.
Let me show what we didn't verify this, but let me show what we did verify, which maybe partially answer to your questions. What we did verify, we asked ourselves the questions that since we, let's think about for gluon scattering amplitude. So for gluon scattering amplitude,
Well, I mean, for n equal 5, not.
no, let's start with 4. I mean, I will tell you what we did verify.
Yes.
So if you start from 4 gluon amplitude, you have coefficient like that, which depend on S over t, and then so we're dealing with the planar limit. So basically, we're talking about diagram which have topology of the sphere with attached legs. And then what we did next, we went to the radial limit. So we considered the limit when t is negative and s much bigger than minus t. So in this case, what you expect from this amplitude that it should be dominated by the contribution of the gluon radio trajectory. So what you expect that the answer will look like follows. So you have some exchange by gluon trajectory, and this exchange will look something like this: s over t in some power, which depends on t, plus crossing contribution. And then, since you know this amplitude to loop level, you must ask yourself the question: what does it give you for this gluon radio trajectory? And then what you obtain for this gluon radio trajectory you obtain all loop expression which looks as follows. So it's gamma cast of A times logarithms T over mu square plus finite path. And this contribution matches exactly what will happen if you start with the calculation by finding and collaborated to loop, keep only maximum transcendental paths, and you will construct exactly some custom of dimension. Then you go to this term, which is a regular one. And then for this term, again, you obtain prediction value to loop level. And then, so far, we know this anomalous dimension to 3 loop level. At 2 loop level, it matches exactly what comes from the Fadden and collaborated calculation in QCD when you subtract only maximum transcendental path.
Yes, but I ask inelastic amplitude, right? Inelastic amplitude,
This
2
one.
to 3, yes.
This one.
And let's introduce two subchannels,
Yes.
S1 and S2. And the question is, S1 and S2 with S2. If you expand this amplitude in the series in coupling constant, then there is such suspicion that there will be simultaneous singularities in these two channels, which is bad, very bad.
We didn't check this yet, but you should also be careful because this calculation, which was performed so far, was calculated multi-color limit. As a fact that during multi-color limit automatically kills the contribution of many rigid trajectories.
It is not rigid trajectory, it's simple analytic properties of Feynman diagram.
We check this. We will check this.
That one is probably killed by the tree-level part, which is in
Huh?
front of the function you're computing.
Real level.
This one.
It's absolute.
So there is
Tree-level.
so it's
It's
this function that you're computing.
Huh?
There is this function that was computed, and then there is a tree-level amplitude which
Born
is
level.
in front of it.
Real level, it doesn't have these singularities. I
Sure,
asked
so that
just
one-
about singularities in these two channels. And
So-
in this multi-rigid limit, they should have.
No, but he's saying that if there is no singularities at tree level, it won't. If I understand correctly, Radu, what he's saying is there is no singularities
Yes,
at
but
Born level.
logarithms have these singularities, and therefore interference of two
Yes,
logarithms.
but if you look carefully in the logarithms become special. If you look for the
Not important.
no, let me draw the diagram.
Sum of logarithms.
Let me finish answering your question. So I'm running a Wilson loop. So the Wilson loop which corresponds to this amplitude, and then it depends. You could write all these kinematical variables, right? Pi, Pj. Then, if you look for the final answer, you will find the final answer does not depend on the full set of the variables. It depends only subset of these variables, and this subset of the variables is just this variable. So you already
What at invariance? It depends on what.
not of all of,
invariance.
not on the all number of the.
Important.
Say
Even
again?
worse.
What?
Yes, I mean, if it depends only on invariance, then I expand this exponent, and
No,
of
but-
course I obtain logarithm square S1 multiplied by logarithm square.
So let's take.
Which is better.
Let's take your example, right? Let's take your example. So I start with your example. I want to define S channel to particle channel, which are just this subchannel. So P1, P2. So this length here correspond to US, right? And then S1 it will correspond to the scalar product with these two vectors. Let's say number 3 and number 4. It will correspond to this one. And then S2 it corresponds to this one. So basically, your point is that if I start looking for the analytical properties of the amplitude as a function of S1 and S2,
Yes.
it should have simultaneous singularities as a function of these two distances.
And S1 and S2, which is bad.
We will no. I'm-
Feynman diagrams do not have such a
we will verify. We will verify. I will let you know.
Anything else?
Could you use Pauli-Villars regularization instead of dimensional to derive conformal property?
Well, you could calculate. You're talking about Wilson loop. Calculating Wilson loop.
That's what identity from you has to.
Well, you may try, but I warn you that the reason, if you look for this correlator which were calculated, if you do calculation of Pauli-Villars regularization, what will happen? The leading term, instead of having double pole, you have log square of Pauli-Villars. But since Pauli-Villars mass dimensional parameter, you should ask yourself will be divided by m squared. And what's special about this relation? You see that if you look for the double pole and you look for the simple pole, in principle, if you expand this expression powers of epsilon, the fact that it's double pole heated with this factor tells you that the residue of single pole involves the logarithms of this particular combination, right? But now what you have here, you have delta function x minus xi multiplied by the function which depends on x minus 1, x plus y. What I want to say is that the fact that you have xi and here you have 2 points means that your singularity is localized on the cusp. So a priori, there is no reason to expect, looking at the diagram, that single pole contribution for this diagram will depend only on these 3 points. It may well depend on other points. And the special feature of the dimensional regularization, I'm not sure whether it holds true in any other regularization, that the residue on the poles is localized on the cusp, which means that all the residue depends only on a single scale with just distances between 2 adjacent points attached to the cusp. And this property is non-trivial. If you do calculation in any other regularization, I'm not sure that you will get this property very easily from each individual diagram.
What's the status of dimensional regularization in equals 4 at higher loops?
In fact, it's not dimensional regularization, it's dimensional reduction. If you want to use, remember in one of my diagrams, I have shown you a diagram which contained insertion into gluon propagator, this one. So if you do the calculation of this diagram in dimensional regularization, you will not verify BDS-ansatz. BDS-ansatz holds true only if you use dimensional reduction. And dimensional reduction is made to conserve supersymmetry. And so far, the status of the dimensional reduction, the explicit calculations have been done in the schemes only to 2-loop level. Up to 2-loop level, we know this regularization is good. And since we did the calculation also at 2-loop level, we're also doing rather well.
Okay. Final question from.
You mentioned in the conclusions that you suspect a link between integrability and this dual symmetry. Could you say something?
So this brings me also to Arkady question that actually the first thing before you go, before you go to this dual conformal symmetry, you must ask yourself the question: what about ordinary conformal symmetry? Because we're talking about scattering amplitude. We're talking about scattering amplitude in conformal field theory, and then if you're dealing with green functions, you know that for green functions, conformal value identity basically tells that you have this conformal generators k mu, and it gives you differential operator very much the same form as I described you before, equal to something. So if you have exact conformal symmetry, it's 0, it's not exactly different from 0. So I told you that we have here some anomalous contribution. At the end, we identify a Wilson loop with the scattering amplitude. And for scattering amplitude, this momenta is just defined as the difference of the corresponding dual variables. So therefore, if you substitute Wilson loop into the relation by the scattering amplitude, you will obtain the scattering amplitude satisfies differential equation first order in x's, which are momenta. So basically, this dual conformal variance gives you differential equation of first order for the amplitude. Now let's think about normal conformal symmetry. I start from the green function, and then I'm going through this reduction procedure to get out of the green function scattering amplitude. Right? So I start from the green function, which are function of the corresponding coordinates, which are coordinates in Minkowski space-time. And then I know the conformal generators acting on x's are given by the same expression. But now when I go from x space to momentum space, I'm doing Fourier, right? So when I'm doing Fourier, what I will do, I will replace x's by derivatives, and derivatives by p's. And since this guy here, quadratic in x's and linear derivatives, at the end, what I will get for the scattering amplitude, I will get differential equation of second order the momentum. Therefore, normal conformal symmetry will give you maximum second order differential equation. But this equation, first order. Therefore, on the way, there was something happening which allowed you to reduce second order differential equation to the first order differential equation.
These are just different, completely different parameters. So could you turn this around and write another equation on your Wilson loop, which will be second order?
This is a good, whether I could write second order differential equation for the Wilson loop.
That original control.
Well, but then what the reason why I have to write differential equation of second order on the Wilson loop conformal field theory? Where this equation should come from?
From this identity between amplitude and Wilson.
So you would, yes, but then if it's so, then you would say that for Wilson loop, let's forget about amplitude. So I'm defining light like Wilson loop. I'm saying I have conformal symmetry which gives me this. But now you're telling me that since there is this duality, I'm supposed to find another relation for the same object in my equal force theory. And if this relation exists, and if it goes atop of this relation, it means that there is additional symmetry.
And we know which symmetry we may expect.
Which one? Integrability. So this just answers the question.